Have a positive verticity, we assume that the verticity is just 1 inside, but we have some negative verticity outside that is denoted by some constant A, and we assume that the A is positive, so that the verticity on the outer domain is negative. And then we use the function, we consider that each boundary can be parameterized in this way, so that if you choose an angle, then the distance between the boundary point and the origin can be expressed as some constants plus a function, and we do the same thing for the outer boundary as well. So we are assuming the R1 and R2 are small, so these two boundaries, they don't intersect each other, and it's close to a disk. But once we have the non-zero R1 and R2, then the verticity is not a radial function. So as I mentioned, in this setting, if we fix the constant A and the functions R1 and R2 that represents the boundaries, then it completely determines the omega, and then we can write the velocity and the stream function, everything in terms of just A and R. So we will think of everything like stream functions of verticity and velocity as a function of sphere A and R. So this is the theorem that I'm going to prove. So I wrote like in a little bit general form, but I will explain why this theorem can imply that there exists the existence of no-radial solution. So it looks very similar to the Kronecker-Rabin-Wex theorem, but there's some differences. First, we assume that the functional is smooth. So we are not going to prove it, but just let's assume that the situation is very nice. So smooth means it's differentiable, infinitely many differentiable in the Gatton derivative sense. If you're not familiar with this, then just forget about it, like just derivative derivatives. And then we assume that if the functional argument is 0, then f is 0. So we have a trivial let's say. Right. And then the second condition is that there is some parameter a star, such that when you look at the derivative with respect to r, and then this is a linear operator from this function space to this function space. So it has one-dimensional kernel and image, but as a map from HK space to HK times HK minus 1. So this is the problematic part, because at the nonlinear level, the function, its image is in HK minus 1, but we gain a derivative. So this df has one-dimensional kernel and image perp, especially image perp, but this HK is compact in HK minus 1. So, like, according to this space, this cannot have finite dimensional image perp. That's the problem. And we are going to assume another condition on this linearized operator. So we assume that the linearized operator can be decomposed into two terms. Here, the first term has this bound. So basically, as a linear operator, its norm is bounded by the norm of f. So here, the linear operator, it depends on a comma r. So basically, what I'm saying is, like, if you have some function f from r and to r, then its gradient of f at x, it's a vector, and it can be thought of as a linear map on Rn. So when we when you consider the action of this gradient on the vector space, the tangent space, then this operator actually depends on where you are looking at the gradient. So here A, R stands for where you look at this pattern. So anyway, the first term, it's the norm as a linear operator is bounded by the norm of the functional. And the second operator, we assume that this is just bounded operator. And then we assume the transversality condition. So if we take the derivative with respect to the parameter and the functional argument, and then we look at this, we look at the directional derivative in the direction v. So here I forgot to say the v is the non-zero element in the kernel. And then this is not included the image. So here we in 3 we are assuming that the linearized operator has one dimension kernel, so there must be one non-zero element in the kernel, and then we just look at the directional derivative in that direction. And then the image has one dimensional image curve, so this one can stand that missing dimension. So then if the functional satisfies these conditions, then we are going to show that there is some non-trivial solution to the function. So before proving the theorem, let's see how let's see how our settings, how the stationary order problem fits in the. So let's check each item separate. So the first one I'm not going to mention, but let's suppose the functional is. The second one is basically let me write them down. So our functional is that if you fix the verticity out to the outer domain and the boundary, then it gives the normal velocity on each domain, say like outer domain. So it's like a vector consists of two components, and in other words, because the nose vector is gradient curve of the string function, this can be thought of as a tangential derivative. Of the string function. So we look at this tangential derivative of the string function on the outer domain and outer boundary and inner boundary. So we have like two components in the vector. Then so we can have this condition, the second condition, because any radial vicinity is stationary. This is like mentioned before. And then let's look at the linearized operator. So let's check if our functional satisfies the third condition. As I mentioned before, so when you compute the linearized operator at the trivial solution, at the radial solution, then that has a form. So this is an operator. So let's look at the directional operator in direction h. Then this was the radial derivative of the stream function, which is a function of I, A, and R, times h prime minus 1/2 times Hilbert transform. Right. So we analyzed this in the Fourier side. It looks like some constants on the outer boundary that depends on A times I n and 0 minus 1/2. The symbol of the Hilbert transform. We have 0, 0, and the constant that represents the radial derivative on the outer boundary times In minus the symbol of the Hilbert transform. Then last time we saw that we can modulate. We can choose A to modulate so that like one of the diagonal components becomes 0, but the other one is not 0. So that this has like one-dimensional kernel and image perp. But as a map from this space to this space, that's because we are looking for the finite energy solution, in which case so that this guy vanishes. Because on the outer boundary, the stream function its derivative is 0. So this cannot. So here, when you look at the second, this second diagonal component, we have a symbol n. So that's why we lose the derivative. But there's no n anymore. So it's the regularity of the image is the same as the regularity of the input. So that's why we have the same regularity as in the input space. So then what about this decomposition? So now in this decomposition, we are not looking at the linearized operator at the trivial solution, but at just a general input. Here, so if we, this has to be zero, because this one is about the trivial solution. So if we look at this linearized operator, then this changes just a little bit, right? Just a little bit. So we have and I'm not going to write the 1/2 plus h. This Hilbert transform, it maps hk to hk. So it changes a little bit, but we expect that this wouldn't change the regularity spaces. So we have another map which can be thought of as perturbation of the Hilbert transform, and this hk, this k is a map from hk to hk. Does make sense? Like, so this part, this k part is going to be our L2 here. L2 is a bounded operator. Okay, I'm going to write as a map to hk to hk. And this part is going to be our L1 of h. And then we see we lose the derivative. L1, we lose the derivative. But we have to show that this L1, its norm is bounded by the norm of the functional. This is very easy. So we need to show this guy, the radial derivative of the string function, is bounded by the norm of our functional here, f. This is basically the Dirichlet normal operator bound, because we know that the string function, this is our omega, and then let's call this out exterior domain to be. Then we saw that the Laplacian of the string function is 0 in this exterior domain, and psi is 0 on the boundary. Psi is 0 on the boundary. No. Let's suppose psi has some function g on the boundary. Then what Dirichlet normal operator bound says, the gradient of psi on the boundary is bounded by the derivative. So this is one-dimensional because the curve is one-dimensional curve. The tangent derivative g prime, so g prime, the norm of g prime. This is a very typical Dirichlet normal operator. Or you can think of it as like, if g is constant, then we have 0 on the right hand side. Then we need to check whether the left hand side vanishes. So if g is constant, then this implies that the maximum principle says psi is constant in the exterior domain. So there, the normal derivative, it vanishes, and because the psi is constant on the boundary, its tangential derivative vanishes as well. So its gradient is 0 as well. And
you need some growth or something.
Sorry?
You need like a bound on the growth or the energy of light.
Bound on the.
I don't know, but I mean, you can't use like just the maximum principle thing.
Yeah. Okay. So I can't use the maximum principle. Yeah. I think that.
Because somehow.
What is bounded?
No, omega.
Because the domain is not bounded. That's what we meant. Because the domain is not bounded, so you cannot really use the maximum principle. Yeah, actually that is true. But yeah, that is true. But here, the maximum principle is possible because the Laplacian of the function in R2, when you integrate this in R2, then this is going to psi, and we are assuming that the psi, the norm, the average of the verticity is 0. So once this holds, then max or mean of the psi cannot be. So its maximum and minimum has to be obtained on the boundary. So like, I mean, it would be better if I could prove this, but I don't think we have enough time. And the proof is just identical to the usual maximum principle theorem. So just you can use the Evans, the PDE proof, and the proof is just identical. So this is actually very necessary. So in general, this is not true, but with another additional assumption, this is true. So we can compose the linearized operator into 2 parts, and the one part is bounded by the normal of the functional, and L2 is just a regular bounded linear operator. And the transversality condition, this, as I mentioned, like I raised the matrix form, but like these constants, C out and C in, they depend on this verticity A, so we can really modulate this constant, and I explained last time as well, so we can actually have this just transfer surface condition as well. So now we are going to like not really prove, but explain how we achieve how we combine the non-radial solution, non-trivial solution for such a functional. So there are several issues. Let me summarize it because there are too many things going on, and then we need to clarify what are the problems and how to manage each issue. So the first one is that the first issue is that when compared to the Kroner-Rabinowitz, this one dimensional image part is different because as a map from HK to HK-1, the image part is infinite dimensional. Okay. So to remedy, to fix this, we are gonna reprove Kroner-Rabinowitz without the Lyapunov-Schmidt reduction. So for those of you who forgot what the Lyapunov-Schmidt reduction, it was that if the linearized operator has one-dimensional kernel and image perk, then we can actually reduce this infinite dimensional problem into a finite dimensional problem. But because we can't have a finite dimensional image perk, we cannot do this Lyapunov-Schmidt reduction. So we are going to prove this here without using that technique. And the second is about the invertibility. Of the operator. So here what I mean, so that will be clearer afterwards, but what I mean is that, so here when you look at the this linearized operator at this point, a star comma 0, then because at a star comma 0, f is 0. So L1 is actually 0, right? Because L1, its size is less than f, but f is 0, so L1 is 0. So actually what we have is that not just DRF has one-dimensional kernel and the image perk, the L2 has one-dimensional kernel and image perk. So without this one-dimensional spaces, this is invertible. If we exclude these one-dimensional things. What I'm saying is if you have a matrix, say 1, 0, 0, 1, 0, 0, 0, 0, 0. Then this is 3 by 3 matrix. It has one-dimensional kernel image perk. But when you look at only this sub-diagonal element, then this is so maybe you can do the same thing for this guy, but actually we have to consider this one as well. And this one actually is very problematic because that one corresponds to this part. And when you look at in the Fourier side, so this is very small. So we have some epsilon, but we don't know whether this is strictly positive or negative because it was 0 at the initial at the trivial solution. So this operator can be say thought of as sign when you look at the symbol, then in the Fourier side, that looks like in epsilon times in minus sine I times sine, something like that. Probably won't happen, but let me forget about it. But because even if this size is very small, epsilon, when you go to the high frequency, then this one is sine. So even if we have the invertibility excluding these one-dimensional spaces, when you look at the high frequencies, this makes the problems. So that's what I mean by this invertibility issue. in this case. So to fix this, we are going to use the concept of approximates inverse. So this will be clearer in a minute. And the third one is the regularity mismatch. Here, what I mean is that the regularity at the linear level and the non-linear level, they don't really match. To fix this, we adapt the Nash-Moser. Okay. Of course, in the actual proof, these three issues, they like just play like everywhere, but so that's why the proof becomes so messy. But just to make our life easier, let's just see how we can like fix each problem like separate. Okay. So when I deal with this Rabinowitz part, I'm going to assume that like there's no regularity issue, and when I do this Nash-Moser, I'm not going to assume that like the invertibility is okay or whatever. So let's see the Nash-Moser first. Before going to Nash-Moser, let's call Newton's method. It's one of the most basic way to find the zero function. So let's suppose we have a function g from some function space 2. Here, y, they are Hilbert space. And then our goal is to find x star, that of x star comes 0. Like just very typical problem. So we all know that how this works. So if you have a graph of G, then first you start from your initial guess, and then you evaluate the function value at this point, and then you draw a tangent line. And this point is going to be your next approximate solution, and then you evaluate the function value g at this point as well, and then you draw a tangent line here, and then you update your approximate solution this way, and then you can see that eventually you can find your solution x star. So this is the Newton's method. More precisely, we set the sequence of these approximate solutions in the following way. So x naught is your initial guess, and then you update your next approximate solution as follows: minus d g x naught inverse of g of x naught xn. So when you just draw a tangent line, and then when you find this point, then this can be exactly expressed as this way. Then just you look at the size of your g at the next approximate solution, then it's very typical to show that this is bounded by dg of xn inverse norm squared times g xn squared. I skip the computations how we get this, but I think this is very typical. So here we can see that we need two requirements for this mechanism to work. The first one is that we need a small enough initial guess. Namely, let's suppose your initial guess is bounded by epsilon. And second is that the invertibility of G. Is operator because we have to consider the inverse of Vg. So let's suppose the Vg inverse, its size is of order 1. Then what do we get? So we have epsilon, size epsilon for the initial guess, but when you update it, G of x1 is gonna be, this is size 1 and this is size epsilon squared, so we get epsilon squared. Then you can do the same thing when you look at the value of G at the next approximate solution. Then we have 1 times epsilon squared, which is epsilon fourth, and then you will get at the next step epsilon eighth. So you have G of xn, its size is epsilon to the 2 to the n. So it's much faster than just exponential decay, but it's double exponential. Okay. So the Newton scheme says that if we have a good initial guess and the invertibility of the linearized operator, then you can find a solution. And the convergence rate is super fast. Of course, we can't use this method because there's a regularity mismatch. So, what makes the problem in the regularity mismatch? So let's change the function spaces to our set. So let's suppose G maps HK to HK minus 1. But DG it maps HK to HK. So that's the same regularity mismatch as you can see in the theorem. So in the nonlinear level, its image is HK minus 1, but at the linear level, it's HK. So from here, we can expect that DG, it's an inverse, is a map from HK to HK. You can just reverse these two spaces. So here, this specific K number doesn't matter. What matters is, like here, what it says is, if you're given an input, then you lose, the image loses one derivative, and the same thing here. For this linearized operator, the image and the input, they have the same regularity. So in this case, like what's the problem? Let's suppose your initial guess, say H100. So you start from H100. And then when you evaluate x naught, G at x naught, then we lose one derivative. So this guy is in H99. And when you invert it, it preserves the regularity. So this whole thing is in H99. So your xn plus 1 is in H99. So when you take one step, we lose the regularity. And when you repeat it, then x2 is going to be H in H98. Or when you keep going, then like you lose the derivative. So we cannot take the infinite, we cannot take the limit because like we lose the regularity at each step. So basically, the Nash-Moser scheme is one of the ways to fix this phenomenon. I think I should have. Okay. So it's the regularity issue. Instead of defining your next step in this way, let's define your next guess in the following way. Minus inverse minus inverse, and then we regularize by using operator Sn. Here I'm going to explain what Sn is, where Sn is a smoothing operator. For example, given a function in the torus, then as n of f, it takes only finite frequencies. So we are going to pick a sequence of number n sub n that converges to infinity, and then we are going to define our guess in such a way, so where by using the smoothing operator. So we project a given function, we project it into the just lower mode. So here are some basic properties. So this smoothing operator. First is that when you look at the HK norm, so let's suppose f is in HK. Well, once you use smoothing, then it's much regular. It's actually smooth. It's regular than HK, so we can take the higher turbulent form, and that is bound by n to the beta. So we have to pay this price. The second is that so this I is just the identity operator. So the I minus Sn, it concerns only the high frequencies of that. Because Sn, it only takes the lower frequencies. So I minus Sn takes only high frequencies. And when you look at the HQ norm, can be bounded by n to the negative beta this time times here for O. Any questions so far? And then let's see how that scheme can give us the convergence to the solution. So first, we look at the difference between two gases, and let's evaluate this at the HK space. So every step, the solution is smooth, so we can take any Sobolev norm for any k. That is going to be dxn times xn m times k. So I just use this here. I moved this xn to the left hand side, and I just took the norm of this guy. Then we are saying that the inverse is good. It's normal size 1. So this, but there's a problem, right? I forgot. So it preserves the regularity. So if norm is bound by S and N of G and N, HK, and then this is gonna be by using this, because we are looking at these xn's in HK space, so we expect that G of xn is in HK minus 1, as described there. So this one has to be HK minus 1. So we have to use this property. So we have this smoothing operator, so it gives you, we have to pay one price, and we can look at this Gn as HK minus 1. Yeah, I think that's enough for the estimate for the difference. And then now we look at how G of xn plus 1 changes. We look at this guy in HK minus 1 space. And I'm going to write this as G of xn plus 1 minus G of xn minus Eg of xn plus 1 minus xn k minus 1 space. So this is just the finite difference, right? And so we added something new here. So to keep the inequality or equality, we have to have the same. We have to add something that we just added. Right? So like I just like put this guy and subtract the same guy and then use the triangular equation. Then, because we are assuming G is smooth, so this is bounded by this guy squared, right? Because when you have x of x, then by 0. Like this is what Taylor's theorem says, right? So if you expand up to the linear term, linear order, then the error is x squared. The error is quadratic. In this case, the error is quadratic, and because G is a map from HK to K minus 1 and smooth, so its norm is bounded by the square of the difference, and we look at this element in HK space. And then we have the second guy. So let's see like what was the difference of this x and plus 1 and x. And we have G of xn minus plus. We have G of xn plus G of xn. The xn plus 1 minus xn is negative of this guy. Negative dxn inverse Sn of Sn. Right? So we get a cancellation. That is going to be dxn minus, we have minus sign, and Sn of gxn. The because you're having the HK minus 1 here. And this can be written as the identity minus S of G Sn. It's HK minus 1. Right? I just like pull out this Gn. So this guy is going to be its identity, and then we have this smoothing operator here. So we look at, we estimate this by using the high frequency, high norm of the Gn. So we have this guy times G xn, it's HK minus 1 plus that. So we just use this guy, the second property. So when you have I minus the smoothing operator, and its HK norm can be bounded by the high norm of the function f, and then we have something very small number because we are assuming the n is large. We call that here we are assuming that the sequence of n it goes to infinity, so we can imagine the n is super large. So we have something small here, but we have the high norm of Gn. Okay. So the two says that of xn plus 1, it's HK minus 1 is less than n. Yeah, xn plus 1 minus xn, it's HK plus and negative beta times G xn k plus k minus 1 plus beta. This is what we get from here. Then now we have to estimate this guy as well. So we are assuming that this guy, no, now we are not assuming. So we write this guy as, because G is smooth in any space for any HK, so we can write it as some constant that depends on beta, but we will fix beta at the end. So I'm going to write just a sub-index beta here at next, below the inequality. This is bounded by HK plus beta. Right, so G is the smoothness from HK to HK minus 1. So here K is just any number, K is not fixed. So you can just replace K by K plus beta and K minus 1 plus beta. So in this case, if G is smooth, then maybe plus constant. Here, what I'm saying is f of x, f0, f prime something times x. The intermediate value here, right? So it's known is the initial value plus prime. It's known times x. This x is gonna be the xn here. But we are assuming that the functional is smooth, so this is over the 1, so I didn't write it here. But that counts this implicit constant beta. Right? And now this xn can be written as summation of say J goes from 0 to n, 1 to n, x J minus 1. So we take the norm of this whole thing, and that is certainly bounded by the sum of the norms. And for each j, the difference is this guy. We have G xj inverse S and J and G of xj minus 1. J minus 1 1 summation into n plus beta and we are assuming that the inverse is good. So the inverse, it's invertible, but it's invertible that preserves the regularity. So we have S and J minus 1 of G x J minus 1 that preserves the same regularity. And but here our starting point is that we want to estimate the k minus 1 plus beta norm of G. So we want to have the same thing because we want to find the recursive formula. So let's use the property, this guy. So let's lose one derivative, then we have to pay one factor of n. Now n j minus 1, we pay this, and then we can bound it by not k plus beta, but h k plus beta minus 1, right? So we gain one regularity, and then we pay this price plus g naught. Okay, so let me summarize. Let's go back. So I'm going to define an to be xn plus 1 minus xn. It's hk norm, and bn of xn. It's hk minus 1 norm. And Cn be the high norm. I'm going to use this notation. So we expect that the Xn converges in this space, HK space, in the lower regularity space. And then actually the limit is 0 in the sense that Bn goes to 0. But we allow Cn diverge. So we allow the Cn goes to infinity. So basically it means that this sequence, it goes to 0 in the lower regularity, but its high mode, it diverges. Okay. So what we get for 1 is that an plus 1, an is bounded by n times bn, right? An is less than n times bn, and bn plus 1 is less than an squared plus n to the negative beta times cn here. And from 3, we get Cn is less than or equal to the summation of j 0 to n of n j minus 1 times c j minus 1 plus some value, but this just depends on k and beta. So let me just call this guy as like just constant, say where you can see, let's say delta k and beta. Say. So delta k and beta is just this guy. So we can just put this guy in here, and we get bn plus 1 is less than or equal to n squared times bn squared plus n negative beta cn, and cn is bound by something here, but let's assume that n is increasing sequence. So we're assuming that nn is it diverges to infinity, but let's suppose nn is just increasing, so that we can bound this guy using the n minus 1, because n of n minus 1 is the largest one among n sub j minus 1 for all j, times c j minus 1, it runs from 1 to n, plus some constants that depend only on k and beta. Now we have to make some assumptions. So I should have erased this. But what was the goal? So recall what we were doing is that G this for all k, and then we want to find Gx star such that G becomes 0. And then as I mentioned in the Newton method part, so we require initial guess is small enough. And then so what's left is to choose. We have to choose the sequence nn that diverges to infinity, and this number beta, so we haven't fixed beta, such that let me under the assumption A1, under the assuming that this guy, the initial data is sufficiently small, this recursive formula, say R1, 1 gives that n converges to 0 and summation of an is finite. Right? What it means is that we are going to choose nn and beta. Then once we choose this nn and beta, then it completes this recursive formulas. And then if we have bn converges to 0, and then the summation of an is finite, what does that mean? That means that the an is the difference between each guess and hk space. That means this sequence is Cauchy sequence, so it converges. So this guy means that xn is Cauchy sequence in hk, so it converges to x star. And then we have bn that goes to 0. That means the limits is the solution that we are looking for. So the picking specific number is very messy. So that's why the national monster papers are always dirty. But there's an easy way, because like in the Newton's method, we saw that Gn it has the it has the double exponential decay. So it was like epsilon to 2 to the n, something like that. So we can expect that this recursive formula has something like something less stronger than this, but like much faster than just exponential decay. So make an ansatz. So to find n and beta, make an ansatz. That n is some constant to the gamma times alpha n for some gamma bigger than 0 and alpha bigger than 1. So if gamma is bigger than 0 and if alpha is bigger than 1, then this exponent, it goes to infinity exponentially fast, and then this is on the exponent place, so the n and it goes to infinity double exponential, right? So with this ansatz, we can expect that because we have the like nn to the negative beta, we can expect that bn actually decays to 0 double exponentially. So we make an ansatz for the form of nn, and then we are going to make another ansatz for bn. It's going to be 2 to the negative lambda times alpha to n for some lambda that is positive. So in this case, this guy goes to infinity, but we have negative, so bn actually decays to 0 double exponentially. And then instead of finding nn and beta, so with this ansatz, we find gamma, alpha, and lambda. And beta, such that this recursive formula R1 holds for all n. Yes. So once we find such the numbers, then we know that the n converges to 0. And actually, for this one, we have to make another assumption that this guy, its summation converges as well. But that condition, because we are having the ansatz for nn and bn here, so that condition can be written in terms of gamma, alpha, and lambda, everything. So we have to find these 4 indices so that this one, for this ansatz, this is at 5, and for this an, it converts, its summation converges. And I'm not going to do that, but that can be done very straightforwardly. So you just plug these 2 formulas into here, and then you can find the number that satisfies it. Any questions so far? I'm sorry. I mean, the national motor, like the notation becomes really horrible, but the idea is very simple. The idea is that like when you do the Newton's method, but at each step you just regularize it, and then you find the right way to regularize it. That means you need to find the right beta, like how much you regularize the solution. But like once you just follow the notation, then it's intuitively easy to understand, but writing is hard though. Okay, so we had three issues. The one was the chronorhabit of this thing. The second was the invertibility, and the third one is about the regularity. So the regularity can be fixed using this scheme, just be regularized at each step. And let's look at very quickly look at the invertibility problem. So I think I should have done this before National Circle, but I think I made a mistake. So anyway, so in this case, we are assuming the regularity doesn't make any problem. So let's go back to the Newton scheme. We want to find star. What's that? G of x frequency. So as I mentioned, we set the x n plus 1 to be x n minus v g of x n inverse of g of x n. There was an interesting that we saw just like a minute ago. But here's the realization. On the inverse of v. So we have to assume that there were two conditions. One was the sufficiently good initial data, initial guess, and the invertibility of this side. But we can replace in this formula, we can replace G inverse by another operator. Let's find the following. I minus v g x n composed with t. And when you look at the size of this operator, the t initial operator, then it's bounded by the size of the function g. So if we have just 0, if it were 0 on the right hand side, then that means the t is the actual inverse of g, right? So if t was inverse, then when you compose it, then that gives you I identity. So like we have this is 0. But we allow this quantity not to be 0, but something that is bounded by the function value at each point. So this is, so here the t is what is called approximates. It's almost like approximates, almost like an inverse, but not really. But with this t, you can just perform the Newton's method in the same way. So instead of using the inverse of dg, now we set the new guess to be xn minus t, and xn equals with g of xn. Let's see how the convergence looks like. So we evaluate so x n plus 1 minus xn, its size. So now we don't care about the regularity, so I'm not using any turbulent index here. So the difference can be bounded by t size xn times g of xn size. So we assume that just t is over the one size. And that's the first thing. And the second thing is g of xn plus 1. And as before, we write this as g of xn plus 1 minus g n minus dg xn times xn plus 1 minus xn. And then we subtract these two guys, and we have to add the same guys here. And then let's take the norm so that we have inequality. So this guy, as before, we are assuming G is smooth. So this quadratic expansion gives you quadratic error plus this guy. You just plug in xn plus 1 minus xn is equal to the negative t times g. So you can replace, you plug that into this part, xn plus 1 minus xn. Then we get g xn minus e g xn equals to t of xn and g of xn. And then we get the size of this. And then the difference, we get this is less than g of xn, so we have g of xn squared. And this guy can be written as I times dg of xn equals to t of xn, and we put our g xn here. Size, right? So we have the common factor gxn here. So we pull that out. So we have I minus dg composed with t, and then we are assuming that t is an approximate inverse, so it satisfies this guy. So we get gxn squared plus this guy is less than g of xn. But we have another g of xn here, so we get squared. But in the end, we have squared like this. So we get g of xn plus 1 is less than g of xn squared. So that's what exactly we saw in the just usual Newton scheme. So we still have the double exponential decay, assuming that the initial guess is good enough. Now the last piece, the Cranach theorem. Without Schmidt reduction. So now we are assuming there's no regularity issue, so I'm not going to think about this part. It has just one dimensional kernel and image. So this is the motivation of the approximate solution, approximate inverse, because the linear operator, its norm is bounded by something, right? So the inverse of this guy is an approximate inverse of this guy, right? Because at the solution, this guy is 0. So without this guy, the inverse of this is inverse of this. So that's what the approximate solution is. So at the solution, when the right hand side is 0, then the operator you are given is the inverse of the original operator, right? But we are not going to care about this, so let's remove this part as well. And then we have just usual Cranach-Rabinowitz. But still, in the actual problem, these like 3 issues, they play all the same at the same time altogether. So we can't use the Schmidt reduction. So we have to do like something else. So first one is that we've been using the Newton's method. So let's put this problem into the Newton's method setting. Basically, in the Newton's method, there is no parameter space, right? So we have to get rid of this guy. So to do that, let's define function of g I'm not gonna even write this HK anymore because the regularity doesn't matter. So I'm gonna write this method from X to Y. So let's define method from X to Y. So that G of R is given by F of so A star. The A star is the star that is here, so that the linearized operator has one dimension cover and H, and plus P of R and epsilon V plus I minus Q of R. So like actually this functional depends on epsilon, where this P is a projection from X to the kernel of P R F A star comma 0. So we know that at A star comma 0, the kernel is one dimensional. So there is a projection. So we denote the projection by P. So, so if you are given R, so if you fix your boundary, then there is a so the one-dimensional component of R, it fixes the parameter space, and the rest, the component of R, it fixes in the functional space. So the motivation is that at 0, we get F of A star comma epsilon times V. So here the V is the non-zero element in the kernel space. So as I'm doing here, right? So at 0, G of 0 is just F of A star times V epsilon times V. But we already know that if this were 0, then we have just 0. F of A star comma 0 is 0. But we have like one step of size epsilon into the kernel space. So this is not solid. This is not of size epsilon, but epsilon squared, right? Because its first variation, it vanishes because we are taking the step into the kernel direction, right? So we take one step in the kernel direction, but because the problem is nonlinear, so to find the actual 0, we have to correct the other components, and these two are for that purpose. Okay. Now we have just a functional defined between just two Hilbert spaces. So now we can use the Newton's method. So to do that, so let's look at the derivative. Before that, as I mentioned, because these two parts can be thought of as just corrections, and this guy, the main guy, is of size epsilon, we can assume that PR and I minus PR, their size is much smaller than epsilon. If you have a plane and because this epsilon v is the solution in the linearized problem, and in the nonlinear problem, just you have very small corrections, right? So these two guys can be will also be very small. So to do the Newton's method, we only need to show that the derivative of this g is reasonable. So let me do that, and then we finish. So you just take the derivative, and then just you can do the chain rule. So once the derivative hits this guy, then we get partial A of f, A star comma PR plus PR, and epsilon V equals I minus P times R. And then we get the projection here plus R of F. When the derivative hits this guy, we get the same thing, and we have I minus P on here, right? But we are assuming that this guy is very small, this guy is very small, so we can let's just forget about these two terms. So we approximate this linearized operator with partial A of F of A star epsilon B plus VR of F A star epsilon B. Of course, the error is going to be like small o of epsilon. So let's just forget about this because the main term is of size epsilon. Then we want to show that this guy is invertible, but without concerning the regular problem, it's enough to show that this guy is onto, right? Because just imagine you have a finite dimensional space. If the linear map is onto, then the injectivity follows immediately. So let's look at this guy, whether this guy is onto. Okay. But the problem is that when epsilon is 0, this guy is not really onto because it doesn't span one-dimensional space, right? Because we have the one-dimensional image curve. So this matrix, let's pretend everything is just finite dimensional. Then we can think of this matrix as something like 1, 0, 0, 0, 1, 1, 0, 0, 0, 0. And so its image space, its kernel is the first two components. But this can compensate. This can be used to span this missing one-dimensional in the image space, because what the transversality condition says is that the transversality condition is partial R on partial A. Just 2 minutes. The transversality is that partial A of D R of F A star comma 0. It's not included in the image of D R of F. So what does this mean? This means that when you look at partial A of F, A star comma epsilon D, that can be thought of as partial A dr fractional derivative in the direction V epsilon V plus small o of epsilon, right? Because the derivative, I mean, this is the what Taylor expansion says. So this guy, this guy is not included in the image. So this guy is not included in the image. So when you look at this guy is something like epsilon. We have some small things like here, but we have like small vector for the third kernel, something like we are projecting, so it doesn't really matter. Like 0, 0, 0, 0, 0. Let's pretend like the other component is 0 because we only care about the image, the missing image space. So when you add these two matrices together, then we actually get 1, 0, epsilon, 0, 1, epsilon, 0, 0, epsilon. So that we have a triangular matrix with non-zero diagonal components. So this matrix becomes actually onto. And that's how we can prove the invertibility of the linearized operator, and then you can do the next, the Newton's. Sorry for going over time. So let's finish here. Sorry, I'm sorry. Yeah. Yes. No, it's not. Any questions or? Thank you very much.